Hello and welcome back. Today we're going to be solving the third problem on NeetCode's 150 two-sum. Given an integer of numbers and an integer target, return the indices I and j such that I and j equals target, and I does not equal j. You may assume that every input has exactly one pair of indices I and j that satisfy the conditions. Return the answer with the smaller index first. Okay, that's important to note. So let's kind of run through some of the examples here. Here we're given a list of numbers, 3, 4, 5, and 6, and our target is 7. Just looking at it, it would be 3 and 4, or 0 and 1. So here, the explanation is given. Numbers at position 0, which is 3, and numbers at position 1, which is 4, equals 7. So we end up returning 0 and 1. In another example here, we're given a list of numbers 4, 5, and 6, and our target is 10. That should be 4 and 6, or 0 and 2. Here we go. And numbers is 5 and 5, and our target is 10, so that would be 0 and 1. So this seems pretty straightforward. I think, where would I want to start? Let's see. So we're given 3, 4, 5, 6. So there are some assumptions being made. There is exactly one solution per test case. We can have duplicates, but we cannot return duplicate indexes. So if we're given like the number 10 here, we can't return 0 and 0. I think that was what was given. So these are assumptions / constraints. What else is there? Okay, let's talk about some edge cases. I think it's important. I know that the problem itself said that there would always be a solution, but in the case that there isn't, what would we do? Would we just return an empty list? So, like, let's say we were given nums, our input was nums is empty, and our target was 1 or 2. I would assume that our output should also be empty, or I like to think that this makes sense. I'm trying to think through if that's the best solution. Either that, or we could just set 0 and 0. But if we were to set it prior to assigning it, that could cause issues. Let's go ahead and just assume that we're going to return empty here. I think it makes the most sense. It should be handled upwards. Or like in a real world setting, we would probably do things like throw an exception and then handle it above. But for the sake of simplicity, let's go ahead and return an empty one here. And I guess the same would apply if no pairs exist. And our target is -1. Outputs pair would be empty. It says, okay, so we can also be dealing some numbers. So we could also be dealing with negatives. So let's kind of view how this would look like if you were dealing with negatives. Let's just say it was like -2, 0, 1, and our target was -1. Our output would be pair equal to 0, and 2, because -2 plus 1 equals -1. Okay, let's talk about a couple of possible solutions here. I think the top of mind, or I guess not top of mind, but I guess the first pass solution that we would think about is the brute force solution. And we kind of ran through it earlier. Essentially, we loop through our list. For every item on the list, we compare it to every other item. And that is essentially has a time complexity of O n squared, because for every element we're comparing it to every other element. In space, we are simply just keeping 2, or we're simply storing 2, or we're simply storing a list of up to 2 at all times. It'll never grow more than 2. Once it grows to 2, we'll return it. So that's really constant. How can this be? How can we optimize this? So is there a way that we could do this in less than O n squared? Is there a way for us to solve this without actually having to loop through it twice? Well, so let's ask ourselves, why are we looping through it twice? We need to be able to compare 3 and every other number and keep track of 3's index. So what if there was a way for us to see if we saw 3 and store and also have its index ready in hand? That's quite obvious. What comes to mind is a dictionary. So a dictionary allows us to track both a key and a value. In this case, when we hit 3, we haven't found a match. We can simply store 3 in its position at 0, check 4, take 7 and subtract 4 and say, have we seen 3? Check the dictionary, we have seen 3. We can then go ahead and return this. So yeah, I think a dictionary makes the most sense for this one, naturally, because we want to just keep track of what has been previously seen, as well as an associated value, which is the index. And with something like a dictionary, it allows us to access it in constant time. So that removes the need of having to look through another list or another pair. So overall reduces the time complexity of our solution. So what this will be is initialize dictionary to keep track of numbers seen and their index. We would then loop through our list, and as we are looping through, store numbers and their index as we visit for return pair if found. And so for this one, our time complexity would be, we would simply, worst case scenario, we find something at the beginning and end. Obviously that's not an example, but that would be O of n. And our space complexity could actually grow to the size of the list, so that's O of n. Yeah, so I guess this one really comes at a trade-off. Do we value time more than space? And oftentimes the case is we probably do prefer time, but it is important to take note of these trade-offs. With that being said, is there another way that we can optimize this? We know that it doesn't say it's sorted, so there isn't a way to, given an array, return. So we have to also work with the assumption that it can be unsorted, and because it is unsorted, solutions can persist at both the beginning and the end. So I'm inclined to think that O of n is our best solution at this point in time. Of course, we could sort, but that would be n log n, which would be still less efficient than this. So given that it is already unsorted, let's go ahead and write this one down, or let's go ahead and code it out. Num scene equals dictionary, and then so we'll name this result equals list. For index we'll call this complements. Complements equals target minus our current number. We would simply just return complements at complement and our index. Else, we have to add our complement to our complements. Or it's not add, it's not a set. Complements at our number and its index. And instead of that, we're just going to return an empty list like what we said earlier. So let's run through our code. So first we initialize our dictionary, which is a list of which contains the complement or the numbers that have been seen and their index. Then we enumerate through our numbers list. We calculate its complement, which is the number that we need in order to hit our target. Then we check to see if our complement is in our complements list. Then we would return the index of our complement as well as our current index, which should be greater, because that was also a constraint. And if this hasn't been hit, then simply put, we add our current number into the complements list as well as its index. And if nothing matches, we just return an empty list, which should never be hit, but keeping it there for sanity check. Let's run through the basic example here. So when we hit our for loop, we see 3. We take 7 minus 3. We take 7 minus 3, which is 4. We check to see if 4 is in our complements. It is not. Then we add 3 and its index to our complements. Then we see position 1, 4. We calculate our complement, which is 7 minus 4, which is 3. If the complement is in complement, so if 3 is in complements, which it is, we'll go ahead and get the index and return our current, and then return our current index. So let's go ahead and run this and see if it works. Cool. We went ahead and passed our test cases here. Sweet. Awesome. I hope that helps. I know I ran through quite a bit here, but just wanted to be a little bit thorough. Yeah, see you in the next one.